Welcome, everyone. Welcome to the FDL-X Heliolab 2024 State-of-the-Art AI Showcase. We're here in partnership with our partners from NASA, Google Cloud, Pasteur Labs and ISI, and NVIDIA. And on behalf of myself and my fellow presenters, James Farr, Jonathan Knowles, and Gabriel Sutherland, I'd like to welcome you all to our showcase. At FDL-X, our teams engage in problems that are not only cutting-edge AI research, but they are difficult, high risk, and high reward, what computer scientists might call non-trivial. In the presentations that follow, you'll see cutting-edge AI research, including advancing continual learning AI for predicting thermospheric density, continual learning AI for global understanding of geoeffectiveness, a virtual mission to monitor the sun and advance the missions to Mars, and finally, a radiation detection method designed to support human spaceflight beyond low Earth orbit. These projects push the boundaries of AI in space science, emphasizing modularity, reproducibility, and real-time applications. Heliolab is an aggregation of emerging AI capabilities, which James will now explain in a little bit greater detail.
Thanks, Anne. So yeah, really great for you to join. We're always excited to do this end of show at the end of our FDL sprints. These state-of-the-art showcases really are state-of-the-art in AI. You're going to see some really phenomenal stuff. Like if you're a machine learning geek, you get to see really like the best of what trusted AI can be, as far as we know. If you're a heliophysicist, you're really going to start to understand the potential of machine learning for studying our star. And you'll hear a little bit more about that in a moment, because we really want you to understand the context of AI and the study of heliophysics, which is really emerging really fast at the moment. So these three projects are sort of all about the relationship between our sun and the Earth, and the interactions of our star on our technologies, but also our aspirations to explore. You're going to see two different flavors of project. There's going to be two quite high TRL, we use this word, technology readiness levels to describe the maturation of AI projects. You're going to see two which are pretty high TRL, and you're also going to see two which are just starting off. They're right at the beginning of their journey. And so, they're really trying to explore and see if there's a sort of weak signal, like a new discovery, which we can then, take to more mature results. So with that as a sort of setup, I'd like to really introduce our colleague from NASA, Lika Guha, who's been with us for over 9 years. I mean, she's really the reason FDL has been successful. She's been an incredible stakeholder. And Lika, I hope you don't mind me embarrassing you a little bit, because I think you've always been able to see the potential of AI a little bit before anybody really, and you've always let us really push the envelope, which is why we're able to be here right now showing this real state-of-the-art work. So I wanted to give you the microphone and again say thanks for joining us, and tell us a little bit more about living inside a star.
Thank you, James. I'm beyond embarrassment at this point. Let's just go straight to the sun. I mean, why do we study the sun? Why Heliolab? And, my response is that this is the biggest, fiercest object in our sky, life giver. What else are we going to study? So, it's an obvious thing to do. And we are using the new tools and technology with our data. We are not only in the midst of heliophysics big year, that is the NASA division level activity, encompassing the two eclipses we have seen, just grand event. And it's going to culminate with the Parker Solar Probe's closest encounter with this star. which is what we are living with. We are living in a star, with a star, and eventually my dream is to live as a star. And you can already see that. I mean, I didn't know whether this is a made up image, real or
No,
not.
this is Lika. This is from this week. So this is our colleague in Antarctica. So they were there and they sent this to us. So
This is
this is
incredible.
yeah.
I mean, I don't have to say very much. We could just be mesmerized watching this. So it's not only heliophysics big year, but we are continuing to head towards the peak of solar cycle 25. That's what we are seeing. The sun touches everything in our solar system. It is Earth's life force, nothing else. We are approaching solar maximum and the sun's activity, as you are seeing on this poor telescope in Antarctica. It's getting bombarded by energetic particles being bathed in this beautiful auroral light. I mean, it's continuing to increase, right? And we want to highlight our star's importance and effect on everything within our solar system and into interstellar space. The Sun Earth connection, which is what our division used to be called, is a vital part of our lives and society, influencing a variety of systems on Earth. And these are things we often don't hear about, but I want to just highlight them. It's agriculture, economics, climate change, politics, food scarcity, as well as the physical, mental, and emotional health of humans. And that's why we had created Heliophysics Big Year, to bring the entire world of, non-scientists, citizen scientists, people to understand what the sun does for us. And of course, we are reminded that all of humankind's space missions, and that's where NASA comes in, including the International Space Station, much of our nation's infrastructure, and not ours. It's global. Communications, surveillance, and navigation, including the criticality of the importance of the GPS system. They are all operating in this environment created and driven by sun's variable emissions, which are basically light particles, magnetic fields. And you're going to hear how we utilize this information that comes through various in various forms: remote sensing observations, in situ observations, spectroscopy, and utilize them to extract insight. So given all of these, identified needs and more, like creating a win-win situation would be to develop various problem centric capabilities. And that was like one of the fundamental goals of the Living with the Star program, science with relevance to life and society, that basically extract maximum value from science data through developing new approaches for combining data-driven methods, modeling, and algorithms capable of machine learning, deep learning. These are things we are continuously introducing in each year of our FDL. And we're doing all this even in the face of limited, weak descriptions or identifications of physical elements and features, because we don't have satellites for like earth science people do, right? We can't surround, or haven't yet done so, surround the sun with satellites. That's when we get more observations and our models, our AI tools become more rigorous. So this year, NASA Heliophysics Division initiated a concept, which is the FDL-X Heliolab. So we are focusing on heliophysics research. It's a derivative of the very successful Frontier Development Lab approach to provide laser focus on heliophysics related research and to orchestrate basically applied AI research and technology for heliophysics applications, building on a body of NASA data and AI pipelines ready for deployment. That's what you're going to see. So I want to just briefly take less than a minute to talk about this particular slide. And I like to show this because people think that the sun affects Earth or space weather happens only during solar maximum. Cannot be further from the truth. And what you're seeing in that picture, basically aurora is something we all see, and many of us have actually witnessed it in May, very recently, as far south as even Boulder, Colorado, or further south, closer to the equator, both from the northern and southern hemisphere. But this picture shows you kind of the variation of the solar cycle from solar minimum to solar maximum. And that is reflected with that white dot. That is the total solar irradiance. That is the radiation budget we work with for climate. And you can see how it varies. It's the variation is very small. It's 1/110%, but that changes a lot of stuff. And below that, you see various images taken from various places of the aurora australis and aurora borealis, which is clearly an indication that a solar storm or a solar event on the sun has made connection with Earth, and it's happening all the time. And I'll end with that, and my best wishes to the team that are going to wow us with all the incredible science and technology development they have done over the 8 weeks. Thank you.
Yeah, and thanks, Lika, and thanks for the great questions. Starts with good questions. And so, yeah, super excited.
Thank you so much, Lika. And on that note, one of the themes in Heliolab this year, as James and Lika have mentioned, is high TRL and observing the best practices there. And so on Wednesday, you got to see our colleague Jonathan in the wormhole, and he explored this with Google Cloud's Scott Pembry and NVIDIA's Rick Karras, and NASA's, and now the White House, John Karts. But we'd like to do this again and dive into this with Google's Massi Mascaro and James Parr to join the discussion. And so, James, if you'll kick it off.
Yeah. Hey, Massi. Good to see you.
Everyone.
Yeah. Thanks so much for joining. I think one of the things I wanted to kick off, because we talked about how, and Lika mentioned, we're focusing on heliophysics, and we have these parallelized projects, which means they're all sort of starting to inform each other. So we're using bits of one pipeline that are perhaps informing another, and we have this tool which is ITI, which allows instruments to be glued together. And so we're sort of seeing the benefits of AI starting to work in concert. And one of the things which really becomes apparent when you start having to get AIs working together is that you have to trust them. And so trust is really, of course, it should be central to any sort of AI methodology or any AI engineering. But for us, it's become extra important because these AIs are sort of working together. So I sort of wanted to kick that off really and hear from your perspective about trust, and perhaps reflect on a little bit those things we talked about how we can learn from how NASA did things during Apollo. And actually, I'll read them out here just so you can have a think as I'm talking, just about this idea of actually simple is sometimes best, simplicity. Test, and then test again. Again, the teams will know all about this because that's so much of what machine learning is. Strict configuration control. Again, this is something which Apollo was extremely good at, understanding if there was going to be a change, this is why, and we're going to document it all. And then lastly, extensive simulation, like really trying to simulate the effect of a model as it interfaces with reality. So with that, I was sort of wondering if you could riff on that, and it'd be great to hear how you're thinking about that with the projects you're working on.
My pleasure, and I'm also kind of a big kind of fan of like the Apollo program and the Apollo approach to kind of solving problems. I completely agree with like the premise here. I mean, AI is a tool, and as any tool that we use, especially in science, we need to be able to understand to what level we can trust and rely on that tool, right? I mean, in the Apollo times, actually kind of reliability was really kind of brought up to the next level, because you were actually putting kind of, humans on top of like a giant rocket, and like you had to kind of make sure they would survive. But in science, actually, there are also a lot of like bad consequences of like bad science kind of inductions and decisions. And so we have the same problem. And I like to think about these problems a lot actually in the context of what happened in the past. Very, very recent, I mean, like very recent is in the last 50 years, right? We actually witnessed a very, very similar kind of phenomenon with respect to computation in science in general, not AI, just computation. Like at the beginning, when the initial, computational tools and simulations came about in science, a lot of folks were completely kind of distrustful. And it took quite some time to build that trust and to build the right procedures to understand both what are the limits of things like simulations and computational kind of statistical analysis and Monte Carlos, and also like to understand how to run them efficiently at the right scale and how to actually kind of make the right deductions. I would actually argue that nowadays, probably like the majority of science is built on computation. And I don't think actually modern science would be possible without the extensive amount of computation we put in it. So we really kind of learn to first adopt, trust, and then master the tool. And I think actually we are in that journey with AI. We have witnessed a lot of like spectacular applications of AI to science. Most recently, I don't know if you've seen the recent work we've done actually on environmental science and climate prediction. Those are things Google, but there are actually many other actors, including NASA, that are working on this. But actually, I think actually we're still kind of in a very kind of lower maturity level, if you want, than what we are in, for example, just kind of using computation. That's why a lot of folks still kind of rely on computation as and simulation as a way to, if you want, keep in check some of those AI prediction, and that's totally fine. I think we're moving very fast though. And one thing actually I'm particularly excited, and I know actually kind of this is also part of like what the teams actually have been researching today, is that just like when we did computational physics and computational in general kind of science, we didn't kind of throw the baby with the bathwater. We actually tried to embed in the computation as much of the physics knowledge we had acquired over centuries. In a sense, kind of refine that in the context of computation. I really love when AI is applied not just on data, just kind of okay, there's a bunch of data, predict me something, but actually when it's actually kind of is embedded actually with the physics knowledge, so that the AI model starts from, say, your hundreds of years of science understanding and physics understanding, and potentially the 50 years of computational understanding, how you run these things at scale and how actually you make them reliable from a computational numerical perspective. And so I think actually that actually is a great direction to go. And also kind of conclude last, actually kind of piggyback on what Lika said about the specifics of like heliophysics problem. I think the thing that fascinates me about heliophysics, apart from all the things that Lika mentioned, is that it's an inherently multidisciplinary kind of topic. In a sense, when you talk about heliophysics, you're kind of going from nuclear fusion and plasma physics, radiation, to atmospheric phenomenon, economy, and kind of electrical grids. Like you really kind of cover the whole spectrum of things. And in a sense, actually, I think that AI has a particular kind of advantage in those problems, because AI is a very kind of powerful tool to connect things together that actually sometimes are from disparate things that we humans sometimes have a hard time kind of really grasping around. And actually sometimes actually we're not trained to grasp around, right? We usually get trained in more kind of limited sectors. And so like I think actually this actually is a really, really kind of fertile ground to kind of do this work. I'm really excited to see what the teams have to report today.
Yeah, actually, Lika, sort of building on that, I mean, one of the things which is sort of fascinating about the sun is it's just so enormous. It's completely outside our sort of perspective. I calculated that the data set from the Solar Dynamics Observatory, which our team's been using a lot, it's 36,000 times bigger than the training corpus of ChatGPT. This is monster data. This is again, why we're so grateful of the partnership with Google Cloud, because really this is a huge scale stuff that we're grappling with. But one of the other things which is sort of fascinating, and perhaps Lika, you could talk to this, is that the way, for example, the solar magnetic field works is completely counterintuitive to our human experience. Like the magnetic field has properties which aren't what you expect. And again, can we use machine learning to sort of discover things that perhaps are outside our intuition?
I think we are actually doing it. So kind of following up on, what Massey and you have just said, it's not just the magnetic field. I mean, most of the physics we deal with are things we can't touch, we can't see. And sometimes even the notion of physics is changing. Solar neutrino that I studied in the 80s when we knew very little, there are again new ideas about it. It's the unseen forces that we try to measure with our observational capability, and then we try to detangle and infer that. And I think what AI has added into that dimension is that when we have done research with just computational tools, simulation, utilizing the vast amount of data that we have gathered, it's not just right now. Over 50 years, it's just not NASA, the ground-based agency all over the world. The ability to kind of gather those data and infer insight from that has been outstanding. And I have supported a lot of ideas of modeling called sun to mud. We call them strategic capability, very physics based and to some extent data driven. And I think when these teams worked on just data from the sun, data from Lagrange point 1, ground-based data of magnetic field on Earth, combine that with sort of, orbit-derived neutral density and connect them and get absolutely amazing results of neutral density, which is a very important aspect of space weather because that's the world most of our technology live in. It just tells me that we have to bring both these forces. We have to bring the scientists to look at this, validate this, benchmark this. This is the future. I want to add one more idea, kind of we understand meteorology, right? And we have surrounded our planet with satellites. So it's not just physics informed modeling, which is a new term in AI for scientists, PIN, physics informed neural network. And meteorologists are beginning to use it. Some of our scientists in the geospace environment are using it. But it's the observations and the assimilative power. So someday we will get that for the sun. I call it space meteorology. That's where we are heading. We can say whatever we want, but if we want to leave, sort of go from being earth dwellers to spacefarers, there are no shortcuts. And AI is going to play a huge role.
Excellent. Well, thanks both. I think that was an excellent appetizer, Lika from the heliophysics perspective, NASA perspective, and Massey from the AI perspective. And again, thanks so much for your partnership. It's amazing having Google Cloud having our back on this work. And I hope you're as proud as we are about what you're about to see. So with that, I'll hand back to Anne.
Wonderful. Thank you so much. And as you just heard from Lika, sun to mud, you're going to see that now with our first team, which is our Geoeffectiveness continuous learning team. Our researchers Opal Isan, India Jackson, Chetrej Pandey, and Vibhuti Kumar Cha. And with that, I'd like to introduce our expert advisor, Alexander Lavin, will introduce the challenge.
In our massively interconnected world, understanding geomagnetic storms is crucial to protecting our power grids, communication systems, satellite ops, and ultimately, this modern society. It is that we are beholden to the moods of our star. Geomagnetic field perturbations are the footprints of its reach, with impacts that are far more serious than dazzling auroral displays. Forecasting the ground impacts of this space weather requires an understanding of coupled physics systems with cascading effects across spatial temporal scales. There's a need for AI or machine learning approaches that can remain relevant by improving over time or learn continuously. It is the Geoeffective continuous learning team here that will extend the capability of chained machine learning pipelines, so-called Dagger and Sheath, with rather non-trivial advancements needed to inject data streams from a variety of sources and deploy adaptive models that become reliable by evolving on the fly. They seek to provide predictions in real time, moving beyond single-use, curated models to an ever-adapting, ever-learning system fit for the future.
Good morning, afternoon, or evening, wherever you are in the world. We are the Geoeffectiveness Continual Learning Team, and we are pleased to share with you our work. Our dream team spans multiple disciplines and domains and includes myself, India. I am our pipeline and web hosting production lead. Then we have Opal, who is our uncertainty quantification and interpolation lead. Next, we have Bubiti, who is our data and code deployment lead. Next, we have Chetrich, who is our machine learning and continual learning architect. And lastly, we have Mike as our faculty and cheerleader. With that said, what is our challenge? Well, the challenge is to see if we can reliably predict geomagnetic storms within a continual learning framework. In other words, we want to ensure that our models remain relevant and improve with the addition of future data sources in geomagnetic storms. But first, what are geomagnetic storms and why do we care? Well, we have solar events and features such as solar flares, coronal mass ejections, and coronal holes that occur on the surface of the sun. These events can produce everything from solar wind to high energy protons and solar energetic particles that travel through the interplanetary medium and come in contact with our geospace environment. This interaction gives us some of the pretty auroras that we see, such as the northern lights, but they can also cause severe damage to our technologically dependent society, harming our power grids, gas pipelines, communications, and space infrastructure, and even astronauts in spaceflight. Ground geomagnetic field perturbations are the direct drivers of the ground effects and an essential proxy for the rest. We need actionable and operational forecasting pipelines to predict these disturbances and mitigate their effects. But this is not the first time we have taken the route of machine learning to develop a predictive tool for ground effects. Previous FDL teams in 2020 and 2023 have already made progress in this direction. This problem was approached by breaking the sun and Earth's connection into two parts. One from the sun to L1, and second, L1 to Earth. As we have observatories at the L1 vantage point continuously monitoring the solar wind conditions, we can use these measurements to forecast the geomagnetic perturbations, which is exactly what the original Dagger was doing, ingesting a stream of L1 data and predicting the ground geomagnetic field. But Dagger only gives us a lead time of 30 minutes, so it does not solve our problem. We need a longer lead time. So during last year's challenge, the team went further and developed Sheath. Now, Sheath is a model that can predict the solar wind parameter at L1 using the data from the Solar Dynamic Observatory. It is prepared by the Analysis Ready data team in the same year's challenge. And with this, we can get a lead time of around 5 to 7 days when fed into Dagger. This year, we have taken yet another step forward, and I will now hand this over to Bubiti to tell us more.
Thank you so much, India. I am Vibhuti, and I will talk about further progress that we made while building upon the foundations led by previous teams. We developed an easily deployable forecasting pipeline, which offer a near real-time live inference with quantified uncertainty. On top of that, we aim to provide the model in a continual learning paradigm. One module suite that does all of these out of the box, we call it GeoCloak. Now, without any further delay, let's open this GeoCloak box and see its building blocks. The GeoCloak box has three key building blocks. The first is Sheath, which predicts solar wind parameters at L1 using STO data as input. The second building block, the newest version of Dagger, operate in two different modes. One that uses Sheath prediction to predict low fidelity ground perturbation at supermax locations with 5 to 7 days of lead time. And the other uses near real-time solar wind data from ACE and Discover to do the same, but with higher confidence but definitely at lesser lead time of around 30 minutes. Both these forecasts are then passed to the next block, where interpolation and uncertainty quantifications are performed, and the results are stored, later to be used for our live inference. Now let's go through these blocks individually to know how these blocks are working. And in this race, Seath is the first one to start with. So unlike previous effort, we have used a multi-layer perceptron model at the heart of Seath. As mentioned, this model takes input from SDO data and forecasts solar wind condition at L1 with 5 to 7 days of lead time. We have developed two versions of this model. One that uses the extracted feature from SDO data, primarily the properties of coronal holes and active region across all wavelengths as input, and other that uses the SDO embeddings provided by our ARD team. In the plots, where we can compare the true and predicted value, we observe that the model are effectively learning the ambient solar wind condition. However, they are less accurate at capturing the peaks in these parameters, which is somewhat expected since we are not including any CME-related information in the model. Now, Dagger, the second block, can ingest Seath's prediction along with near real-time observation from ACE and Discover to further proceed in the pipeline. Chetraj will be explaining this in more detail. Chetraj, over to you.
Thank you, Vibhuti. Now I will be continuing our presentation by discussing the Dagger model within the context of continual learning, which is how to make sure our models remain relevant and are fit for the future. To quickly recap, as you can see in this figure, Dagger is an RNN-based model designed to time series data of solar wind parameters from ACE and Discover at L1. It then predicts geomagnetic perturbations at ground stations and uses an interpolation scheme to issue global forecasts. Continual learning for our project falls in the category of domain incremental learning. Our main objective with continual learning is to ensure that as the new data becomes available, the model can be retrained without losing its performance on previously used data. This is especially important since in a typical continual learning scenario, models often suffer from what is called catastrophic forgetting, where new information overrides what the model had learned previously. To tackle this, we introduced two strategies into our Dagger CL model. First, we employed a data resampling strategy. During each retraining stage, we randomly sampled 40% of the instances from the dataset used to train the model in earlier stages, as shown in the figure. This allows the model to revisit some past experiences without overexposing it to the entire earlier data, which could lead to accumulated bias over time. Second, alongside resampling, we integrated a loss penalty approach known as EWC. It identifies important model weights after training on the initial dataset and preserves them during subsequent retraining stages. When new data is introduced, EWC applies a penalty to ensure these important weights don't change significantly. This enables the model to adapt to a new data while retraining crucial knowledge from earlier training, allowing it to perform well across both old and new datasets. Our evaluation shows promising results for Dagger in the CL paradigm, as seen in the plot, which tracks the model performance at each stage of continual learning using the same validation dataset. There's consistency in the performance and also improvements to a degree across our three evaluation metrics, MSE, which is also our loss function, root mean square error, and mean absolute error. The lower plot demonstrates that the performance remains stable with minimal fluctuations throughout the three stages of continual learning. Finally, here is an animation that shows the output of our Dagger model trained within the continual learning paradigm. It shows the predicted geomagnetic perturbations of the north component at ground stations. And with that, to further elaborate on the predicted outputs of Dagger, I will hand things over to Opal.
Thank you, Chetraj. So our aim is to make predictions of global geomagnetic field perturbations via sparse supermag magnetometer forecasts. There are less than 600 ground supermag stations, and they're spread around the globe, mainly located in the Northern Hemisphere. We approach this problem using a machine or statistical learning technique, namely Gaussian process regression. This technique assumes Gaussian noise and priors, in a linear model. We can therefore predict the global mean and standard deviation of each geomagnetic field component via a closed form expression. For the linear model, we use spherical elementary currents, which is a physics-based model that mimics the ionospheric current flows. And after rigorous comparison with other empirical and physics-based model, we found that the spherical elementary currents were the most accurate and certain. So overall, we were able to successfully predict geomagnetic field perturbations globally with quantified and reduced uncertainties. All this comes together in a GeoCloak web app, which is fully accessible to the community. This portal contains a dashboard with near real-time geo-effective data and predictions. This dashboard you are currently seeing is the real-time Dagger CL inference, which displays geomagnetic perturbations predictions around the globe for the east and north components, along with their standard deviations for quantifying their uncertainty. Our model is running on a remote virtual machine that is updating every 5 minutes based on our solar wind data from ACE or Discover and Dagger, with the outputs being pulled into the portal for visualization. GeoCloak provides an entirely new way to incorporate machine learning into operational space weather forecasting, and these efforts provide actionable forecasts for global ground geomagnetic perturbations for decision-making with quantified uncertainties. It also provides near real-time online inference in GeoCloak, which allows the community insight into our latest geospace conditions. And finally, GeoCloak is the first step towards geomagnetic continuing learning operational forecasts. This new paradigm ensures that the models remain relevant, improve, and are ultimately able to take advantage of new data, whether it's from new missions or solar maximum. And on that note, thank you everyone for listening.
Wonderful. Thank you so much, GeoCloak team. It was amazing to hear. And with that, our next team is our thermospheric density team. The thermospheric density team is Jordi Villa-Perez, Aishara Kumar, and Will Fawcett. And our expert advisor, Tom Berger, will introduce the challenge.
Satellites around our planet provide communication and internet and connect our world. But collisions are an increasing problem, especially in low Earth orbit. Thermospheric drag, which is the braking force exerted on satellites as they orbit the Earth, is a major factor in predicting where spacecraft are and when collisions might happen. Thermospheric drag is highly influenced by the sun, specifically solar irradiance, and the drivers of geomagnetic storms. Understanding and better modeling these relationships gives mission managers improved estimates on numerous aspects of spacecraft management. The Thermospheric Density Continuous Learning Team has expanded Carmen, a data-driven AI pipeline which can significantly outperform state-of-the-art models used in satellite operations. The goals are twofold: to build a continuous learning system through live ingestion of solar drivers and satellite data, and to better enable forecasting, updating Carmen's abilities in an ever-changing and more congested space environment.
Hello everyone, and welcome to the presentation of the Thermospheric Density Continuous Learning Project. This FDL-X Heliolab project has been developed by our team of researchers and faculty members, myself, Jordi, Aishwarya, Will, Sankalp, Giacomo, and James, with a variety of expertise in the domains of space weather and machine learning, including data science, astrodynamics, and computer science. The challenge revolves around the life of satellites in the low Earth orbit, responsible for providing communication and navigation solutions while subject to the effects of the thermosphere and solar activity in a very congested environment. Thermospheric drag is one of the driving forces acting on satellites in the low Earth orbit, and it has an enormous impact on their trajectories. As you can see, the demise of these satellites shown here, and therefore is crucial for collision avoidance. The main driver of satellite drag is thermospheric density, which in turn brings the major source of uncertainty in its prediction due to the influence of different space weather phenomena. These physical phenomena are directly caused by the interactions between the Sun and the Earth. Different processes associated with solar activity interact with the Earth's upper atmosphere and with the Earth's magnetic field, influencing the ionosphere and thermosphere. The effects of some of these different processes on the upper atmosphere can be observed in this animation. At first, we see the different layers of the lower atmosphere. When we zoom out, we can see the thermosphere, which expands and contracts according to the day-night solar cycle. But we can also see all these fluctuations near the poles, which are caused by a strong geomagnetic storm and its interaction with the Earth's magnetic field, showing the complexity and variety of events affecting the thermosphere. In this context, the goal of this project has consisted of developing a data-driven solution that provides thermospheric density predictions that enhance the safety of space missions and improve the operational success. All that by leveraging data from satellite missions as it becomes available. Therefore, turning the challenge of dealing with this congested upper atmosphere into an opportunity for devising improved thermospheric models. And to understand how we're going to do that, let's take a step back and see how this is done in the lower atmosphere. Weather balloons play a crucial role in obtaining distributed measurements that are then used to make accurate weather predictions. However, we don't have weather balloons that can get to space. Or do we? Weather balloons in our case are none other than satellites, which were not originally designed to measure thermospheric density, but that now they can provide us with these measurements alongside with their original mission. In particular, by means of such density measurements, satellites are able to inform our models in order to improve our upper atmospheric predictions. This task has been accomplished throughout the years by means of Karman, a data-driven model for the estimation of thermospheric density. Karman has shown enormous success, outperforming state-of-the-art thermospheric models. In this year's effort, we have expanded Karman's horizon, developing a continual learning approach that permits, first, the live ingestion of data from satellites and different physical drivers, and second, a continuous update of the model, enabling improved density forecasts. Now, I will hand it over to Will, who will put this work in the context of machine learning technology readiness levels.
Thank you, Jordi. Previous iterations of Karman sit at level 3 and 4 of development. Through our efforts this year, we have transformed Karman into Karman Continual Learning, or Karman CL for short. And in the next few slides, I'll show you how we did this. In order to reach this higher level of development, we've had to build an autonomous data ingestion and continual machine learning pipeline using Google Cloud Platform. It is this pipeline that gives life to the continual learning and live density forecasting capability of Karman CL. As you can see, this is a little complex, so in the next slides, I will break this down. The first component in advancing Karman to higher technical readiness levels is the design of a live ingestion data pipeline. This pipeline automatically pulls data from 11 different satellites as soon as that data becomes available and provides us with an ML-ready data input that is key to forecasting thermospheric density. But what are these inputs? They are satellite data, including our target densities and the corresponding time and positions, the solar and geomagnetic indices, solar wind parameters from Omni, solar irradiance measurements from SOHO, and model-derived density from MSIS. In addition to this, the pipeline is created using some software called Terraform. This software allows us to effectively template sections of the pipeline, which allows us to quickly and easily add new parts should new satellites or other sources of data come online. The data ingestion pipeline is now running live. So what happens when we acquire new data and want an updated forecast? The first thing that happens is we check the new data against existing distributions. And this is what you can see depicted in the two plots here. If the data is consistent, as shown in the green box, then we follow this arrow and use our existing Kalman model to give us the density forecast. But what happens if the data distribution is different, as shown in the red box? This automatically re-triggers our training of our ML models. And we don't just have one of these, but an entire zoo of different algorithms. Once trained, we compare their performance against each other and select whichever is best and use that to get the density forecast. This newly trained model then becomes the new default for the next set of data that is acquired by the pipeline. And now I'll hand over to Aish, who will talk about the results.
As Will mentioned, we would like to demonstrate what Common CL can do. And here we are showing you exactly that. This is a global map of the forecasted densities at the top of every hour for 3rd February 2022. I'd like to highlight two things here. These forecasts are for a day of a month, which is completely unseen during training or validation. And two, we have a forecasting lead time of 100 minutes. So we are predicting 100 minutes before an event occurs. We also see that the model captures the bulge in thermospheric density, which follows the sun, giving us confidence in our overall predictions. As you saw earlier, our pipeline is flexible and supports many different inputs. This allows us to run different experiments, like checking input importance and the effects of changing lag and resolution. Let's look at how input importance affects performance. In this table here, the green and red traffic lights show you the inputs that have been included or excluded in some of these experiments. We're highlighting a few cases here, and essentially, the lower the MAPE metric that you see on the right side column, the better the performance. If we focus on the bottom row, we see that the more the data, the better the performance. However, if you look at the second to last row, we see that just including two inputs, SOHO and Omni, gives us nearly similar performance. Now we can also run experiments by changing the length of the time windows. And what you're seeing here on the left is the change in performance for different time windows. Green is the best performing time window and red is the difference relative to this. And we see that as time window increases, performance degrades. Similar to time windows, we can also experiment with the history lengths. And here we see that this has less of a drastic effect on the MAPE metric, but in general, longer history results in better performance. Now, I'm going to pivot for a moment to talk about a major solar event that happened this year. To give some context, the sun goes through an 11-year solar cycle, and we are currently in solar cycle 25, and we are in fact at the peak of this cycle. In May of this year, there was an X-class flare, and maybe some of you remember the effect of this, which was auroras that lit up our skies. However, it also kept spacecraft operators on edge, as you can see from this news headline. So the question we asked was, can Kalman CL foresee this event? And let's look at the answer. So indeed it does. If you look closely at this animation, the little red dots are forecasted densities for this May event with a lead time of 100 minutes. And the shaded orange region preceding the forecast is the historical information we've used to obtain this forecast. And you see that it does predict the sharp increase in density. Now at the very end, we overlay the model predicted densities from EMSIS for comparison. And we see that the EMSIS results are not only worse, but they couldn't have been obtained in advance because it does not have predictive capability, whereas Kalman can provide 100 minutes of lead time. Overall, we are able to forecast and anticipate change in density, and as a result, we could potentially provide adequate warning to satellite operators of an incoming event like this one. To summarize, we've developed a new thermospheric density model that can meet space operation demands, and it also outperforms empirical models in accuracy. We've extended Kalman for forecasting and implemented a continual learning framework with live data ingestion, continuous model updates, and real-time inference. So what does this mean in the bigger picture? With this tool, we will be able to possibly avoid thousands of spacecrafts maneuvering at the same time when we are hit by a geomagnetic storm and avoid consequences like collisions or unsafe re-entry of satellites. To wrap, I would like to thank the FDL-X Heliolab team, our public and private partners, and all the reviewers who have provided us with invaluable feedback.
Wonderful. Aish, Jordy, and Will, such amazing results. In Seattle. James, next up we have our panel.
Yeah, just wanted to say thanks to the teams. That was really awesome. I have to say, you know, when we started on this journey, putting our toe into continual learning, I didn't quite expect that the results would be so sensational. And I'm sort of sitting here slightly blown away, and I hope the audience is as well. You guys saw a lot of stuff, but what you just saw essentially, you know, two of the biggest problems we have, and showing how essentially virtual magnetometers can be distributed across the world and provide that real-time service, but also this ability to predict the way our thermosphere behaves in advance of a flaring event. I mean, that is incredible, and so I really wanted to invite our colleagues up to just reflect on that, and you know, so great to have such a good community of experts, and we wanted to invite a few up just to talk about the work. And we've got Bashi Ferdowsi, Tom Berger, Massey, who we met before, Lika, but also Mike Haynes, Giacomo Arancini, and James Walsh, who are sort of behind the scenes making it happen. But yeah, I'd love to get your impressions. As I said, I'm really blown away, but I'd love to hear what you guys think.
Are you going to call on us, or do we
I was thinking, yeah, I was going to pick on Tom. You're usually pretty good on the spot.
Thanks, James. Yeah, I'll talk a little bit about the Thermospheric Continual Learning Project, because that's the one I was most involved in, and the importance of that. Right now, the current state of the art in thermospheric density modeling is based on an empirical physics-based model developed in the 70s, which is data augmented, so it is pretty good for a modern model, but it's still based on really basic empirical modeling, and it does a good job at nowcasting. In other words, the current state-of-the-art model for thermospheric density forecasting, which is used in collision forecasting for space traffic management, is really good at sort of telling us what's happening right now. But what's lacking, and what I think this thermospheric density team has made a big step forward towards, is a forecasting capability. So looking forward at least 100 minutes, hopefully more like a day eventually, to predict what the thermosphere is going to do once we have a large either solar flare event or geomagnetic storm event, is really the key to the future of space traffic management. So right now, everybody's sort of working with what they've got, which is nowcasting. I think what you're showing here is using machine learning, we have the ability to advance this into a real forecasting capability, which, by the way, the physics-based models also struggle mightily with. There are physics-based models out there which try to forecast these quantities as well. They all show large biases and or scatter noise. And so I think we're on the right track here using a data-driven model to get into a forecasting mode for thermospheric density.
Thanks, Tom. Massey, is that giving you time to formulate some thoughts? Be good to hear about the geoeffectiveness work as well.
Yeah, no, I mean, I think, you know, both works were stunning. I mean, on the geoeffectiveness, I was kind of both impressed by the result. I would actually kind of add on, and this actually again kind of goes with both projects, the idea of using continuous learning here. I think it's really the next step, right? I mean, a lot of these processes, they're not very hard to simulate, as Tom mentioned, from a physics perspective, but they're also kind of intrinsically chaotic. And so like kind of having that kind of, you know, continuous loop where the model is able to adapt is very important. And also like things actually change. Like, actually kind of, the Earth is changing. So like, I mean, having that adaptation is really kind of, bringing this to the next tier level. I love actually the way in which the teams actually have approached it. I think actually kind of the other aspect I would call out is that it's actually awesome also to kind of optimize these processes to kind of be computationally efficient. The more kind of computational efficient you are, the more actually not only you can kind of run those actually kind of faster and better and more frequently, but also like you can think about kind of scattering them and kind of having kind of more data and more locations where you run them. So I love actually kind of how the teams actually also approach that problem specifically.
Bashi, so good to see you, although you're fading in and out. What did you make of it? Loved what inspired you about the work?
Yes, sorry, I'm just going back and forth. I'm not sure what's going on. Yeah, I was amazed with both teams, as Massey said, and because I've been long involved with Geoeffectiveness, I mostly focus on that. I'm so amazed that they have this new app. I think that would be one of the first new things that gives us live forecasting for magnetic field perturbation globally. This is neat. Like imagine May 2024, if we had that already, we could have like predicted what's going on where on the Earth. So that was really impressive for me. In addition, I think that gives opportunity for future missions and future installation of magnetometers. So those nice, like you saw, perturbation that you saw on the global picture of the Earth, that we could determine what is the distance do we really need to have the magnetometers to have better accuracy in the future. And with the Karman, is amazing that 100 minutes forecasting in advance. That's like great for future missions and like launching satellites. So I'm impressed with all the works that has been done in only 8 weeks.
Yeah, thanks so much, Bashi. So sort of speaking about, so good to have James and Mike and Giacomo here. What did you learn from being, deep in the weeds? I don't know if you guys have got some thoughts on that. Mike, do you want to jump in?
Yeah, I mean, I think the challenge this year was really, really cool to take things from the sort of single-use curated data. Let's get a model, let's make it work, and then take it to this continual learning framework. So I learned a lot about continual learning, how to even approach it as a problem. It's not trivial at all. And the team, the amount of work they've done behind the scenes to understand the problem firstly, and then to actually action and implement, phenomenal stuff. But yeah, I also just wanted to reiterate this future focus, and I think that's something that really is so exciting. We're going to have more and more data streams. We're entering this era of like mega constellations, more missions going to the sun, going everywhere, going to the moon, Mars, and to be able to ingest that, leverage that, and make machine learning models, AI models available and relevant into the future. Cannot wait to see what comes from that.
Yeah, I wanted to reiterate that because, of course, we looked at the literature to see if there was examples of continual learning, and there isn't much. So what you're seeing here really is the tip of the spear. And again, Giacomo and James, same question really. What was your reflections on sort of being deep in the weeds?
In my case, I would say I was very impressed also, like in general, by the use of transformers. Like there are these new models that can handle static features, temporal features, and future values, and like all these different data come together, and the model is able kind of to handle it and to establish very well what are the parameters that you need to learn and how to tune effectively the model to make the best out of this. And I was very impressed when we compared this in a continual learning setting with respect to, for instance, pure LSTMs or like kind of old models now. It was incredible, the difference in terms of, forecasting accuracies. So that was, to me, really impressive, and I learned a lot.
How about you, James?
Yeah, I mean, I can only add to that and say that there's a couple of things we've certainly learned. One is, pipelines are hard. Having live data coming in is hard. Making sure that that's correct. you could get anything at any point, and you need to do sanitation, validation. You need to make sure this is consistent. There was a lot of effort put in, and that's where the sort of increase in TOL was a bit of a big gain, a big learning process for us, because that's what you need in order to make sure that this is going to keep on working. And then when we're talking about sort of CL, well, that was a huge sort of additional learning curve, which continual versus continuous, what's in which field, what to which academics say is which with the other. And I feel like we really sort of took something from industry, and I think it was like, hey, this is where industry practice can be a really great process, a really great value to the later stage scientific process, and say, right, well, this is how they look to be doing it. Maybe they're using recommender systems and they're A/B testing, and they're doing this on a completely different data set that isn't scientific. But how do we adapt that to this and get the same level of benefits? And I feel as if like this approach has sort of been a huge step towards that, and it's a really curious way of both needing to do that industrial task, being very scientific about what is your trigger, when are you doing these retraining tasks, and all the sort of mathematical sort of certainty and uncertainty with that in relation to the pipeline. So yeah, I think we learned quite a lot.
Thank you. Lika, I'm going to give you the final word. Amazing to see these two projects back to back. I'd love to get your take.
Well, I think I have come to expect miracle in this 8-week window. It is absolutely stunning. To me, continual learning is like continuous learning. That's been the journey through this very simple partnership that was established a decade ago. And this is revolutionary to me. I will invoke a new word that came to mind as I saw this is AI to operations. In NOAA, Parler, or DOD, or NASA, we are trying to really improve the space weather prediction, right? And that improvement comes with forecasting. And we call this domain research to operations. Well, let's call it A2O. AI to operations. And let's use the word augmented intelligence, because this is nothing but that, what you're demonstrating. I think I want to inject few other things already, kind of what you have demonstrated with both models, right? More data will make it better, more accurate. The other thing that I'm finding, which we had not integrated in the AI domain, when I say it's sun to mud model, I'm not joking. In the beginning of Living with a Star, that's the premise we started with. This is a connected system. And we did these assimilative models and empirical models and all of that. But integrating the solar input in this fashion hasn't happened. And that's where AI is making such a fundamental breakthrough. Even though we have been collecting data, it hasn't been assimilated in the AI form this way. And that is huge. And kind of breaking it down into its component pieces really would be awesome for scientists to interrogate, what's missing in their physics. This is not a one-way street. So just like we learned from the empirical assimilative models in the past about physics, this opens up that window. As Tom just mentioned, right, that physics-based models can't address all of this. So these are amazing tools that is being kind of opened to the science community in the spirit of open science. All of you are sharing all of this. To me, this is just heartwarming. Thank you so much for all your work.
Thanks, Lika, and thanks the panel. You're representing really a sort of fleet of experts behind the scenes that have helped the teams. But really, I wanted to take a moment to thank the teams, because I realized the level of engineering that we've all just seen is relentless. It's a lot, and we're just extremely grateful for how hard you've worked. So thank you, and let's change gears and go to the next group of work.
Thanks, James. As you've just seen, the previous two teams were working at a high TRL level and involving existing tools with continual learning. But now we'll see two teams that are working at a lower TRL on cutting-edge new research. So the first of these teams is the spectral irradiance of the 3D sun on Mars team. And our researchers, Brianna Isola, Rituparna Kurt, Christoph Schoeninger, Marcela Schonsky-Ibero, and Gautier Bardi Difar2 will come up. But first, we will have our expert advisor, Angelos Bordres, introduce the challenge.
How much energy the sun shines on all planets is connected to the 3D structure of the solar atmosphere, as it is shaped by powerful magnetic fields. For a long time, we have focused on studying 2D images, and mainly from Earth's perspective. Reconstructions of solar activity from any angle are essential for better understanding solar dynamics. As humanity sets its sights on Mars, anticipating the sun's influence on the Martian environment becomes crucial for the success of future missions. In the future, models like this might also be able to inform satellite operations, communication systems, and the safety of astronauts. The spectral irradiance of the 3D sun on Mars team is building on the foundation of previous FDL work, taking advantage of novel AI methods that integrate data from the latest generation of solar observing satellites. The result is a virtual observatory that allows scientists to probe the solar corona, the outermost part of the sun's atmosphere, as it extends its reach to Mars.
Hello everyone, we are spectral irradiance of the 3D sun, in short, spies on Mars. This is our multidisciplinary team, including heliophysics and machine learning domains. I am Marcela, and together with Christoph, Brianna, Ritu, Gautier, our faculties Robert, Ben, and Andres, we will show our project goals, experiments, and outcomes. Solar activity can impact the Earth, posing challenges for our satellites and astronauts. The sun emits extreme ultraviolet light, in short, EUV, which impacts Earth's atmosphere and can degrade the orbits of satellites, increasing the risk of them falling back to Earth. To protect these assets, it's crucial to estimate the sun's energy emissions in the form of EUV light, known as irradiance. From Mars' perspective, for instance, the solar irradiance influences atmospheric dynamics, including temperature fluctuations and dust storms, contributes to atmospheric loss, and affects surface conditions, impacting both potential life and exploration missions by altering radiation levels and power generation capabilities. Improving our understanding of the sun dynamics and physics can help us to connect it to other stars and star-planet systems. By studying the sun in detail, we create a reference point that potentially improves our understanding of other stars and then planetary systems, contributing to the search for habitable worlds.
The core philosophy of our project is to maximize the science we can do with our current constellation of satellites. Currently, we have a few satellites orbiting the sun with different instruments that don't always measure the exact same thing. We want to use AI to unify them. For instance, 4 satellites are taking images of the sun in extreme ultraviolet or EUV light. However, only one of them is still capable of measuring the irradiance, which measures the energy of EUV light emitted by the sun. Additionally, they don't necessarily take images of the sun with the same wavelengths that we can see as color filters, giving more information on different regions of the sun that have specific temperatures. In order to better understand the sun and its potential impacts on our assets in space, we need more viewpoints with a complete suite of instruments. One idea could be to launch more satellites. However, in this study, we want to explore how we can use AI to learn from all the data already gathered by the existing satellites and build virtual satellites or add virtual instruments instead. These virtual satellites could be placed anywhere in the solar system, giving us an estimation of novel views of the sun. Additionally, by learning the relationship between the EUV images taken by the satellites and the measured irradiance, we will be able to enhance all the satellites with a virtual instrument estimating the irradiance. So here, the question is, can we generate virtual observatories that view images of the Sun and estimate irradiance at any point in the solar system, including Mars? To answer this, we apply AI to create 3D model of the Sun that can provide multi-viewpoints from anywhere in the solar system, and then give us the possibility to estimate solar irradiance working as virtual instruments.
So in order to generate 3D representations of our Sun and estimate solar irradiance at any point in the solar system, we take the following steps in our spectral irradiance of the 3D Sun on Mars pipeline. First, we use 2D images with a set of wavelengths, represented by the different colors here, from multiple spacecraft at different positions in space. Our SunEarth model then combines this information to resolve the Sun as a 3D object. This allows us to estimate physical quantities with density and temperature in the solar atmosphere. From this, the 3D model then provides us with novel perspectives of the Sun, such as unseen views from the solar poles, but also from any point in the solar system. In combination then with a second neural network, which we further developed from previous FDL challenges called MaxAI, we can feed the images from the novel perspectives to estimate the solar irradiance at Earth, Mars, and at any point in the solar system.
Let's embark on a virtual journey through the solar system. Imagine we're in a spacecraft, starting from our home planet Earth, traveling through space, and ending at Wonder Planet Mars. Imagine the screen in front is our instrument panel, where the left element shows our current location in the solar system. On the right, we have a live view of the Sun from our spacecraft, which changes as we move around it. On the lower left, there is an irradiance meter that tracks how the Sun's irradiance changes as we move through space. This varying irradiance, represented as a full spectrum graph, is a key result from our SPICE team. Here we see the Sun in different colors or wavelengths, which offers a glimpse into the different layers of its atmosphere. Seeing the multi-wavelength 3D view of the Sun from any part of the solar system is another innovative result from the SPICE team. As we continue, we can choose to observe the Sun's temperature, density, and where the energy is coming from in the solar atmosphere. This is the first time that these quantities have been measured in 3 dimensions. Finally, as we approach the red planet, we can see the Sun from a Martian perspective. The irradiance monitor now shows the solar irradiance as measured from Mars. This blend of rotational 3D views of the Sun, measurements of its physical quantities, combined with changing solar irradiance along a hypothetical path from Earth to Mars, built taking advantage of our constellation of satellites, is the result of our work this year.
But how can we now validate and show that our 3D and irradiance model of the Sun represents physical reality? Well, our method provides unprecedented views and that there are currently no direct observations for comparison. Instead, we make use of a physics-based simulation of the Sun from the solar eclipse in April earlier this year. This allows us to validate our 3D model using the simulation and simultaneously the estimation of density and temperature in the solar atmosphere. To validate our irradiance estimations at different points in the solar system, NASA's Solar Dynamics Observatory mission provides us with irradiance measurements from Earth's perspective. The orange line in the figure on the right-hand side shows the actual measurements, and the blue line our irradiance estimations. As we move towards Mars, we will be able to compare our irradiance estimation from the 3D Sun reconstruction with actual irradiance measurements from NASA's MAVEN mission, which measures solar irradiance from Mars perspective. This will allow us to directly compare our irradiance model with real measurements from 2 points in the solar system.
As we reside inside the atmosphere of the Sun,
It is critical to understand its features and large-scale properties. Orbiting satellites have provided never-before-seen images of the solar corona and other solar features. We can now take advantage and enhance these observational resources by utilizing artificial intelligence to simulate views where satellites do not exist. Here, we leverage NASA's satellite missions, without which our work would not be possible, that provide views of the sun from different viewpoints, as well as in different wavelengths, to create a novel 3D model of the sun. Now we can study multidimensional solar phenomena and inform future missions in space, such as launching a constellation of satellites to get insight on key positions around the sun. By learning and integrating data from multiple sources, we can enhance the capabilities of satellites in space and inform future missions. Speaking of missions, humankind has already sent tens of thousands of instruments into space, both robotic and human-driven, that continually get more advanced and far-reaching. In this current age of space exploration, we are in need to understand the space around us and how we can protect ourselves and our technology to enable unrestricted scientific discovery. Here, our model uses the capability of our satellite fleet to create virtual satellites that can estimate quantities from any point around the sun, including Mars. Our virtual irradiance instruments can also be added to any EUV imager, enhancing our current capabilities to capture solar activity. Our approach not only extends to heliophysics, but lays the foundation for future coalescence between real observed data and state-of-the-art computational methods. It is not without the Stereo, Solar Orbiter, MAVEN, SDO, and all the instrument teams that make projects like ours possible. Thanks to them, we can use AI as a critical tool to aid and protect our future missions to the Moon, Mars, and beyond. We want to thank the Predictive Science team for sharing their MHD simulations with us, all of our commercial and AI partners, our faculty mentors, and the community of the Frontier Development Lab. We look forward to what discoveries lie ahead. Thank you.
Wonderful work, SPIES team. Thank you all so much for that great presentation. Next up, we have our final team. The final team is our forecasting radiation exposure for human spaceflight with researchers Elena Marsara, Kimberly Sinclair, Xiaomei Song, and Rutuja Gurov.
With Artemis and future missions to the Moon and beyond, NASA is about to send astronauts into deep space for longer periods of time than during the Apollo era. Therefore, understanding radiation dose in space matters more than ever. Predicting radiation exposure is key to protecting our astronauts. Ionizing radiation from the sun can increase dramatically during coronal mass ejection, solar flares, and energetic particle events. If they have early warnings of exposure, flight controllers can advise the crew to shelter in protected areas or change the mission flight plan to reduce exposure. The Forecasting Radiation Exposure for Human Spaceflight team is using solar observation data and radiation dose data from spacecraft dosimeters to develop methods to minimize the biological impact of radiation on the human crew. Modern machine learning methods allow us to integrate solar data and spacecraft radiation measurements to forecast radiation exposure. This work has the potential to make deep space flight safer for future astronauts.
Hello, everyone. I'm Rutuja Gurov, and I'm pleased to present our work on forecasting radiation exposure for human spaceflight. This is our fantastic team. We are 4 researchers. Elena is a cosmologist. Kimberly is a planetary scientist and astrobiologist. Xiaomei and I are machine learning experts. Ed Brown is our guest expert in heliophysics and machine learning. And our faculty advisors are Bala, who is a heliophysicist, and Ganesh and Matt, who are machine learning researchers. Space, let's get into it, shall we? Space is filled with radiation. As we are living with a star, that's a ball of magnetized plasma. On Earth, we are protected by the magnetosphere of our wonderful planet. However, as we venture beyond low Earth orbit, leaving Earth's protective shield behind, we are exposed to the space radiation environment. The radiation space has two primary components, the solar radiation in form of solar energetic particles and the galactic radiation in form of galactic cosmic rays. This radiation is harmful to assets in space, humans, and instruments. Predicting radiation doses beyond low Earth orbit locations is increasingly relevant to us because we are going back to the moon and venturing beyond Mars and onwards. To set the scene, let's fast forward 6 years. It's the 2030s, the Artemis missions are well underway, and humans are developing a presence on the moon. You're one of 4 astronauts on the Artemis 5 mission doing a routine maintenance on the Lunar Gateway space station that's orbiting the moon. Everything's going great. You're almost done replacing a malfunctioning sensor when, all of a sudden, millions of miles away, a massive solar flare erupts on the sun. Protons with energies greater than 10 million electron volts are shot like bullets out of a gun directly at you. These protons can penetrate your spacesuit, damage your DNA, putting you at an increased risk for cancer, cardiovascular diseases, and potentially cause irreparable damage to your central nervous system. So what can you do? Well, let's rewind to 30 minutes ago. You were feeling good, blissfully unaware that the sun is about to shoot you full of protons. Wouldn't it be nice if you had an early warning of this incoming radiation threat? You could save yourself. You could go into the Lunar Gateway and shield yourself from these incoming protons. That's where the amazing folks at NASA's Space Radiation Analysis Group, or SRAG, come in. They monitor the space radiation environment and provide in situ radiation information to the crew in a nowcasting setting. To support SRAG's efforts in providing reliable radiation data to the crew, in our project, we explore taking space radiation monitoring from nowcasting to a forecasting setting to be able to plan and adapt mission activities proactively as opposed to reactively. With that, my colleague Xiaomei will take us now with how we tackle this challenge.
Now, let's talk about how we make all of this possible. It all comes down to data, real-time, precise, and from every angle. To predict space radiation, we began with the sun. Goes monitor X-ray give early warning of the solar flares, while SDO captures detailed images that reveal the magnetic activity behind the solar eruptions. But it's not just about the sun. We also track radiation in space with Biosentinel, which monitors changes as Earth obeys the sun, and Crater, which provides vital data from lunar orbits, crucial for missions beyond Earth. All this data fit into machine learning models. This model needs lots of data to learn patterns and make reliable predictions. The more data, the better our forecast. Here, we can see images from the SDO capturing different wavelengths of the sun's activity. These snapshots show us where and when the solar eruptions began. Hotspots that can release enormous amount of radiation into space. Below these images are 2 crucial graphs. The first shows the absorbed dose rate, recorded by Sentinel. The second, from the Crater instrument, shows the absorbed radiation dose from lunar orbit. You can see the sharp increase in radiation following a solar flare. This is why the SDO dataset is crucial for our predictor mission. However, forecasting radiation is a challenge for several reasons. Firstly, solar activity is not fully understood. The sun cycle became low and high activity, and the complex physics behind these cycles make prediction difficult. Solar particles influenced by magnetic fields and turbulence move unpredictably, making our prediction even harder. Secondly, radiation prediction relies on machine learning, which needs a large dataset for accuracy. While we have quality solar observation and radiation data, our instruments are limited, with less than 1% of environment exceeding safe levels. This makes model training challenging, so we must use every bit of available data to improve our prediction. With that, my colleague Elena will take us through our results.
Forecast future radiation, we build an ML algorithm that takes as input radiation measurements from BioSentinel and solar images by SDO, and we consider all these quantities in a window of time that here we indicated as the past. We send all these inputs through the model so that we can predict what the future radiation level will look like. And here are our results. The model predicts different scenarios for the future radiation levels that here are shown as red lines with their mean indicated in black. And you can see that the model predicts that there will be an increase in radiation levels within the next 24 hours. And this is consistent with what BioSentinel is going to measure, which is the blue line. So our model is able to predict that there will be harmful radiation within the next 24 hours, is able to capture the overall shape of the radiation profile as a function of time. And some of the scenario that is outputting predict that the time for the onset of harmful radiation is going to be just a few hours away from the true time of onset of harmful radiation that is measured by BioSentinel. So this is a first attempt of building a forecasting model, and it's already very promising. Indeed, our model can be used to alert astronauts when in the next 24 hours there will be harmful radiation incoming into their location. And we can redo the same exercise, but one day later, when we have already measured that there have been an increased radiation, and we can ask again the model to predict the future radiation levels. Here are our results. Again, the red lines show the different scenarios, and you can see that the black line, that is the mean of all these scenarios, quite well reproduce the measurements from BioSentinel. And so our model can accurately predict the time where the radiation will go back to safe levels, and it can be used to tell astronauts ahead of time when they can exit their shelter and resume their activities. Finally, we can look at this video that contains all the prediction that you have seen in the previous slides and many more. We created this video by sliding the past and future windows across time and asking the model to make prediction from the present time onwards. And so overall, our model is able to be an early warning system when the radiation levels are low. And when the radiation levels are already high, it can be used as a method to inform astronauts on when the environment will become safe. And with this, I will hand it over to Kimberly, who will talk about our achievements and our future plans.
Thanks, Elena. So I'll be summarizing the novel milestones we've achieved this year in our groundbreaking project. We first created SDO-ML Lite, building on past FDL sprints that have developed SDO machine learning datasets, and we've made it more user-friendly in order to enable BioSentinel predictions. We've also curated machine learning-ready radiation dose datasets, such as BioSentinel and Crater, which can now be built upon in coming years in FDL. And we've also obtained preliminary results for radiation forecasting with our groundbreaking work. Having gone through the milestones achieved, I'd like to lay out our next steps and future plans. In our next steps, we plan to release data sets, code, and pre-trained models to the broader community in order to encourage community participation. We'd like to publish our work in papers with exhaustive evaluations of the proposed models. And eventually, we hope to develop a proof of concept live prediction system, with the end goal of this project someday to create a real-time tool and deploy it in future crewed spaceflight missions. So this tool would look similar to a weather forecast on Earth, allowing astronauts to anticipate space weather before it happens. So if you're imagining the scenario we spoke about at the beginning, but with the astronaut now pulling out their radiation forecast handy on their arm to warn them of an incoming event, enabling them to seek shelter in order to protect themselves from harmful radiation. Now, to bring it all back to why we're here, we want to first thank the experts who made this work possible, including Sylvain Costes, Kirill Grigorev, Christopher Light, Janet Barzia, Jack Miller, Nathan Schwadron, and many more. And with humanity's return to the moon in the coming decades with Artemis and the Lunar Gateway, we need to protect our future astronauts. So building this machine learning tool to forecast radiation dose can enable long duration spaceflight beyond low Earth orbit and expand science and exploration into the broader solar system. So we want to thank you so much for listening and have a lovely day.
Wonderful, amazing work, radiation team. I feel like our astronauts are already safer from what you've done. Thank you so much. And with that, I will invite James back to the stage for our next panel.
Hey, yeah, just to concur, I think that work was enormously successful. And, you know, I've been wanting to work on human spaceflight since I was about 7 years old. And even if I get to do it, you know, in the slipstream of the great teams, we're just so proud of your efforts, and thanks so much for working so hard over the last 8 weeks. So with that, it would be great to bring up some special guests to talk about the achievements of the team. And so I'd like to invite Sylvain Coates, who's our stakeholder from NASA Gene Lab, Angelos Voroladis, of course, Lika, who met before, Bruno Sanchez, Andrade Nuno, apologies for the name there, Gunas Baden, and Andres Muniz Jaramillo, just to reflect on what was achieved. It's pretty exciting. And so perhaps I'll sort of start with a question. First of all, like kind of, you know, what inspired you, and perhaps, you know, you could talk about what this means for human spaceflight. And Andres, I know you're always pretty good on the spot, so I might pick on you first.
So I think one of the things that really is showcased by these two teams is the integration. The integration that we're doing. So NASA has a heliophysics platform, like observatory, that is made of many, many satellites. And they are measuring different things. They're measuring something here, something there. The idea of integrating this truly into the actual physical quantities is one of the things that inspires me in these challenges. And something that where you can also kind of like aspirationally connecting with the other teams is that as these satellites comes and go, to be able to incorporate them and integrate them into these pipelines, so that now we have this continuous monitoring that we can use for any and all applications.
Bruno, I know normally your work is AI for Earth, but I was so inspired when we found out that your previous life was in solar physics, and I'd love to get your take.
Of course, actually, you don't know this. I've known James for a while, but you might not know that Angelos, right here also, is the person who hired me right after the PhD. He received a call email from me to say, hey, I want to work with you. And he invited me to the US, and that's where I did my postdoc. So shout out to Angelos. I'm super fond of the time working with him. I did my postdoc in bulk in actually extreme ultraviolet, which is very relevant for the first project. And it genuinely made my month to see him here. So kudos to have him there, and really bring a smile to my face. Having said that, I think both of them are extremely interesting. As you say, my latest work after I left solar physics was more AI for Earth, sustainability, carbon stocks, blah, 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 these things. It's such a fresh air to come back to this field and either search the rigor that is involved here, the complexity of the physics that is involved here. It makes it harder because it's not only you need to understand deep learning and all of the things of deep learning, but also you need to understand the physics that are happening here, which is, I would argue, intrinsically much more complex to what we see on the surface of Earth. So it's been a pleasure to hear this stuff. On the first one, I would say that this is really interesting, and if the focus is what Angelos was saying in the beginning of preparing for going to Mars and life of the astronauts, and so I wonder if focusing more on the total irradiance and not the reconstructions themselves of the 3D reconstructions of the sun at those wavelengths, it's something that you need as a latent space for the irradiance, because then it's the irradiance that is going to be important for how the atmosphere of Mars, which is much weaker, react to that, to understand the effects on that. So I wonder if that's something to consider, that the loss function of the machine learning should not over index on the 3D reconstruction, but on the total irradiance. I noticed in the graph that the mention was to NERF, using NERF for the reconstructions. And I do wonder, I've been wondering this since I heard of it, the Gaussian splatting might be a better approach, because if I understand correctly, the NERF is a 5D space, so every point in the space has a luminance and opacity, but in Gaussian splatting, it's literally like if it were the atmosphere of the sun, because it's composed of little points in space with opacity and characteristics, which is literally what you want to reconstruct when you talk on in the spaces. So that inversion becomes much more natural to the architecture of the machine learning. Having said that, I think the team is in a great position, and kudos to that. If they want to know more, happy to talk to them. On the second one, same thing. The what they do, it's in some sense really hard, because the events, as they say, is a 1% extreme events, but also those events tend to be interrelated if they are close to each other, because it's not the same if it's the first event or the second, and the space of the environment in which occurs changes, especially if you also consider the orbits. Like if they are on low Earth orbit, also the atmosphere the astronaut is different. So maybe trying to attain a lower goal of, instead of regression of the forecasting of the whole timeline, just an alert of shelter, not shelter, shelter, not shelter, which seems a classification which might be easier for the machine learning to pick up, because then it allows you probably to have a longer windows of input method. That's something that I thought about them, but in both cases, I think the problem is very clearly explained. The potential is really clearly explained, which is really important in machine learning, to know what you have and where you go. And it seems that both teams are really strong in their path. So kudos to those.
Thanks, Bruno. I wanted to give the mic to Sylvain. Sylvain, you helped us shape the challenge for the radiation work, and I think we knew when the team started out that it was a really tough open problem, but I'd love to get your reflections on it.
I think the team did a great job, and they show a lot of creativity. I think the one little piece that they added that we didn't think of that I think made a huge difference is adding the images to the data set. We kept talking about dosimeters and gathering all these dosimetry data, but then they brought in these images, and I feel like this was the element that really made a difference in their computation. So I think that was a great pivot that the team put together. In the context of this work for the future, I think it's just the beginning. It's a great first piece. In the context of NASA, I think it's a very attractive project because it brings together the biological world. This is the world we live in. I'm the project manager for Open Science for Space Bio. And so we brought in some of our data on the dosimetry from some of our hardware. And then now, bringing this together with the Helio data, you suddenly start getting even more power. And so I think it shows the cross-disciplinary power of these kind of approaches. So, that would be my big view of the project. And again, I can't wait I was texting as they were presenting Kirill to see how we're going to integrate some of their curation process into our system so we can continue building this AI readiness on our side. So, thinking about our API and how we could provide access to curated data for AI readiness, not something that may be visible for the public, but accessible for the programmer. So, and then as we there's a lot of hardware coming our way. We know Artemis is coming along. So we expect to see a lot more data coming to RadLab, the database that stores this info. So I think it's going to be very interesting to try to plug in this work into the bigger ecosystem we live in. So I think that would be a good summary.
Thanks, Sylvain. Angelos and Lika, I'm going to leave you to the end because I want you to see if you can synthesize what it means to have a 4D representation out to Mars and a dosimeter. But Gunas, just in the interim, I think we knew that this radiation challenge was really challenging from a machine learning perspective, and it'd be great to get your take on what was achieved.
It was. So I hope you can hear me. Let me know otherwise. So yeah, the radiation challenge, I think it was one of the most difficult things. I've been supervising in FDL. I've been a part of this for 7 years. It's been really difficult to get it to the point where we presented these forecasting results. And I think something I can say that actually connects to what Sylvain said is that the SDO images were actually instrumental in getting that forecast plot. We actually have a version of we've done ablation studies. We compared the exact same pipeline where I replaced the SDO images with random data during training. We want to keep this exact same architecture, and it completely killed the forecast. Without SDO images in that forecast figure, there's a flat line. And with SDO images, there's this early prediction type of hopeful thing. We didn't have this in the presentation, but it's a very important science result almost, because we wanted to keep this presentation not so technical. But I'm very excited to just understand what's going on there and I don't know, present it to the community. And we've been I think most of the time we had was spent on figuring out what we can do from a machine learning point of view, dealing with dataset creation. We've been very lucky to talk to people at SRAG and RadLab and SEP Scoreboard, all the people their current workflows. And I mean it's been very challenging, but I'm very happy about the result, that we have something that gives us hope. Further in the year, I think we will have stronger results to share. So I'm looking forward to that. And if I can quickly say something about the SPICE work, it's really exciting because there is a lot of work going on in the machine learning community, especially on the computer vision side, all these sorts of generative models with vision and images and videos and all of that. I think the STO dataset is so vast, high quality, high resolution. There is a lot of data there. It's completely underutilized. I mean, we are doing our best to change this, but I think it's what they've done is a really, really good. I mean, it makes me really happy to see you can take this modern computer vision stuff and just use it for science. It's really inspiring. I just want to share that.
Thanks, Gunas. Just to say, if you say it's a hard problem, I think it's fair to say that it is.
Yes.
But and for those who don't know, Gunas runs the Machine Learning for Physical Science workshop at Europe, so he gets a really good sense of what hard looks like. But again, just thanks so much for everyone's hard work on these things. But so Angelos and Lika, I'm going to perhaps leave you to sum up. And I don't know if it's possible to answer that question about the synthesis, but it seems to me there's something there.
So yeah. I'm going to jump in because I want to kind of address what Gunas mentioned and Sylvain mentioned. And, this has been the goal. For the longest time in Heliophysics division, we have taken measurements everywhere, and SDO is something else. This is the biggest data volume, as James mentioned earlier already, but it's impossible to integrate. And so the way the data has been integrated by the science community is just kind of seeing the data through a soda straw. And what kind of science do we get? We get the science we got. And that is changing. So if you want to go in any of these topics, from nowcasting to forecasting, we have to utilize all of the SDO data. And I'm saying this because we are actually taking that approach. So all the data everyone has used so far, it's the 512 by 512 SDO data. Data we are taking is 4K by 4K. It's IMAX quality. So think of what is embedded in there and what's that's going to do to future modeling efforts. And so we have undertaken the effort of really creating this SDO foundation model right now and seeing all of these different pipelines. Some are already on their way to benchmarking and some are kind of new right now, what it is going to do. And I kind of really wanted to bring this up because where we are going by incorporating images is from nowcasting to forecasting, a more predictive world, which is what science with relevance means, which is what operational agencies want. One more point, and that's for Bruno. Bruno, we will take you back in solar physics any day, anytime. So you go, Angelos.
Yeah, I already have a project for Bruno right now.
Awesome.
Yes, I send them an email in Slack. So the synthesis for those two projects, because the synthesis is the planetary human exploration beyond the Earth magnetosphere, right? To even think that that's achievable without risk to the astronauts, we have to put some minimal capabilities in place. And one is predicting the most energetic SCPs, for sure. And the other one is to see where we cannot see, right? See in Mars where we have no assets now. So I think that's what both of these projects are going after, kind of like illuminating the invisible in our, or the invisible gap in our capabilities right now to protect the astronauts. So that would be my headline that you asked for. Now for the SP Spice, I guess I will call it, is of course my favorite project since we started that a few years ago. And I think that will be, while the irradiance itself, as Bruno just mentioned, is not really that critical for the astronaut health, there are the things that we're going to do the next year's FDL. And this is, we need to bring in flare prediction, which is, that's how you use 3D, well, that's how you use the EUV information to know if there's going to be a flare. And therefore, if you have that EUV information farther away over the Mars, then you can inform astronauts en route to Mars or on the surface or whatnot. And similarly in the lunar space. So that will be sort of our next step. For the SCPs, that's tough. The SCPs are tough because we neither have the physical knowledge, not the number of events that we need to train models. And so this work that the team did, is putting really the basis for us to see what new ideas we need to think out of the box in this case. They had a good idea, of course, they're using models to artificially enhance the amount of events, which I think is definitely the way forward. The other one is to think what other parameters out there, what other data set within this heliophysics system observatories out there that we're not using. Of course, is the white light chronographs, that's one. But there might be other ideas. So that will make a really good challenge to the community. I think mostly the solar community in this case, to come up with something out of the box thinking that can build upon the work that the team did this year, I think. So this is how I'm envisioning us going forward.
Can I add to what Angelos just said? I think very important, as you know, all the community members are here, right? In the way sort of the Dagger model evolved with Sheet, I think we have those tools already in hand. And what we have to incorporate are those tools. So we can't do SCP, peak intensity, total fluence, or progression. That's what we need. And we can begin to utilize CME data, right? Speed, location, width, all of that. So actually, in a way, there is almost like a ready-made topic sort of ready to happen.
Yeah. Which brings us to Bruno's project. So the missing point is what we started with Bruno in 2010 is to connect the 3D view of the sun that we got for stereo to the in situ solar wind, so that we can actually derive the magnetic connectivity, like indirectly. And back then we didn't have all these capabilities. It was very difficult, but right away we saw those where the models actually were failing. You know, we're seeing different things on the sun than what you would expect from what you see in situ. So I think that would be another good FDL project, is to now use all this SDO and 3D basically information on the surface and try to connect with the in situ data and try to predict what is the magnetic field line shape, which then the SCP models can go right on top of that, because the SCPs follow those lines, and so that will sort of build up our capability to hire TRL.
Yeah, what are you doing next summer, Bruno?
Yeah, you see.
Anyway, I just wanted to say again to the teams, it's really hard to take on a project which is at right at the beginning of the TRL journey, and you really did dive deep, and the results are super inspiring, and we're very proud of your work. So thank you so much. And again, faculty and advisors and everybody on the panel really couldn't do it without you. The great questions from Gene Lab and other places, and so thanks so much. And with that, I think we'll hand it back to Anne.
Wonderful. Thank you, James. And if I can have my screen brought up as well, and Gabe on the screen. Awesome. So as you just heard from James and from all of our panelists, the work that we've seen today has been amazing. The presentations really showing the work of just the inspiring hard work of our teams. And FDL is driven by this innovative spirit. I think we already know some of the challenges that are going to come next year. But at the same time, at its heart, FDL is about community. And so I want to take a moment to, first of all, thank our collaboration coach, Belina Rafi, who guides this community with her magical sessions on the 6 C's. She helps us build collaborative culture through community, courage, curiosity, compassion, co-creation, and comedy. And throughout the sprint period, the teams come together as a community of researchers to collaborate with each other and to solve these grand challenges. They support each other and make lifelong bonds while learning to think from new perspectives. And we celebrate this spirit with our yearly collaboration awards. These are our tokens of recognition for excellence in the most important aspects of the FDL community. However, the task of determining who will receive these awards is arguably the most difficult challenge of the entire program. Each and every one of the Heliolab faculty and researchers at some point during the sprint have demonstrated the qualities we look for in the awards. So while ultimately we did have to make a decision, I want to know that every one of you, faculty and researchers, should be enormously proud of the strong work and dedication you've brought to the program. So without further delay, our first award is the most dramatic pivot. So pivoting is an action taken when new opportunities arise unexpectedly. Sometimes this means starting completely from scratch after much commitment has been put into one idea. The Most Dramatic Pivot Award represents the ability to thrive through these changes in directions. Even though they might sometimes be unwanted, they are certainly necessary.
This award will be going to Vibhuti Kumar Cha. So Vibhuti, when faced with an integral challenge goal of the Geoeffectiveness continuous learning team not materializing in the closed weeks, he took it upon himself to drive development and ensure that all data streams and model assumptions are valid, retraining and improving on previous performance. This brave push has helped get the deliverable right back on track.
Our next award is the steely-eyed operator. This person has their eye on the prize. They know where they want to go and they know how to get there. A steely-eyed operator leads their time with a singular focus and tenacity and doesn't balk at roadblocks.
And this award goes to Benoit Tremblay. So in his work on the spectral irradiance of the 3D sun on Mars team, Ben has determined to make sure we never cut corners and validate all our results. He understands and has made his priority to do this, even if it's not the most glamorous part of the project. He has also shouldered a significant part of our effort, never balking at challenges and obstacles.
Next up, we have the unexpected discovery. So just like dirty dishes helped with the discovery of penicillin and melting chocolate bars triggered the creation of the microwave, the Unexpected Discovery Award represents that ability to stumble upon a breakthrough. As Plato once said, science is nothing but perception.
And this award is going to Opal Isan. So Opal, while exploring the interpolation techniques needed to make the Geoeffectiveness Continuous Learning Challenge applicable, went above and beyond what was asked of her. We now have a physically defined basis function that incorporates uncertainty and provides insight into the model itself. Seeing things such as the inclusion of the vertical component of the magnetic field and reducing the effectiveness of modeling has directly informed modeling efforts.
The Heroic Comeback Award is an acknowledgement that when discovering something genuinely new, you have to first fail. But that's only one half of the story. Simply failing isn't enough. Getting back up, learning, evolving, and trying again is how legends are made.
And this award is going to the Forecasting Radiation Exposure for Human Spaceflight team. When faced with a bold new challenge, yet to be explored data sets, compute and modeling challenges, all with limited time, the Forecasting Radiation team has come together to deliver a first-of-its-kind result. Each researcher was vital to this result. Ilana Massara and Kimberly Sinclair for unlocking scientific interpretations of radiation forecasting, Xiaomei Song for connecting the team with relevant researchers while acquiring domain knowledge, and Rituja Gaurav for engineering excellence and attention to coding detail.
The Collaborative Spirit Award is the representation of FDL's beating heart, interdisciplinary research. It supports the idea that to achieve great things, 2 or 20 minds are better than one, and the exchange of knowledge is key.
So this award goes to the Spectral Irradiance of the 3D Sun on Mars team. The SPIES team, as it's known, has been an example of collaborative spirit this summer. They have a wide range of skills that complement each other but have little intersection. They have been determined to stay together and teach each other as they progress through this challenge, in spite of the temptation to specialize and fragment.
And our final award is a new one for this year, the Apollo Award. The Apollo Award celebrates the same engineering excellence that got us to the moon and safely back to Earth. In the era of applied AI, making substantive contributions to space exploration, we need stringent engineering standards in parallel with innovative AI to ensure that our AI-enhanced science is both safe and trusted.
And this award is going to Will Fawcett. The Thermospheric Density Continuous Learning team was tasked with extending the Carbon tool to make it accessible to the scientific community now and in the future as more data becomes available. Will was a true champion of this goal, writing code that is both atomic and broad, pushing the envelope in engineering capabilities while maintaining the highest code quality. Congrats, all.
Congratulations to all of our award recipients, and I will now hand it back to James to close us out.
Thanks, Anne, and thanks, Gabe, for your duties as the award meister, if that's the right way of describing it. Yeah, just to close, you know, it's so awesome to see these projects back to back, and of course we get to see the meal being made behind the scenes, but it's always super inspiring, you know, goosebumpy to see the work come together. And really it's the sort of coming together which is the fascinating thing for me, because we've really tried to understand what high TRL AI looks like, and we're learning a lot, but it seems this incredible synthesis of capabilities, like the ability to have these analysis ready data sets, which are projects in themselves, working with tools like the ITI project, which powers the SPIE's work, and now the continuous learning. This is all a sort of incredible nexus of capabilities which are sort of starting to come together in really exciting and special ways, and it's unlocking all this potential that we didn't even quite realize. And so it's amazing to see this sort of happen in front of our eyes, and hopefully that was inspiring for you all as well. So it's really, I think it's, you know, there's a science story, but also there's a sort of emerging AI engineering story that we're learning as well. And so, of course, we couldn't do this without our colleagues at Google, and just so grateful for the team always helping us behind the scenes and giving us the resources to do this. Like the work you see here today takes enormous compute, and just having these, the ability to spin up many GPUs simultaneously and have these enormous data sets, delivered around the planet with is really an amazing thing. So grateful for the team at Google, and of course Pasteur and Alex Lavin and the team there really helping drive state-of-the-art in continual learning for science. As I mentioned before, this is the tip of the spear, and Pasteur have been amazing partners for us in helping understand what that looks like. And then, of course, NVIDIA, who've been there at the beginning, this amazing partnership that we've had, which really, you know, started off the journey, and now we've been doing it for 10 years. So very grateful for NVIDIA too. Also, just wanted to shout out, obviously, Lika. We couldn't do this without NASA and the great challenges you bring. Mike Little, for all your wisdom and friendship. Hunju as well, for those incredible conversations that really help us make sure that this is scientifically relevant. It's great to have you guys supporting us. And sort of lastly, I think, you know, sometimes we say an AI isn't just for Christmas, but perhaps another way of saying it is, you know, it takes a village to raise an AI. I don't know if that's going to become a T-shirt or not, but I think you understand the sentiment. Really, there's a lot of people behind the scenes, and thanks so much to the all the folks who've been there and provided advice. The Trillium team behind the scenes, led so amazingly by Anne Spalding. Thanks so much, Anne. And Belina, who, as we said, you know, interdisciplinarity is hard. It needs glue, and Belina does such a good job of making things stick together. And then, you know, the faculty, it's sometimes we forget about them. They're in the background making it all work. They're doing the planning. They're making sure that the challenges are beautifully shaped and the data is ready, and then the teams make their deadlines, and we're so grateful for the work you do. And then lastly, the teams, you know, just for coming on this ride with us, taking it a big jump. It's a leap of faith to, you know, come and work on projects like this, which are so difficult. And you've done it. You've made us proud. You've done incredible things. And so with that, we'll finish off and just say, ad astra per algorithmus, and we'll see you next year.